this. Yeah, so I hope you've all seen the My Place notification or the Teams message. I've released the coursework. So I see a few of you have forked it already. I'm not invited to all the repos yet, but it might be harder than you imagine. So if you get started early, you can gauge whether you're going to be in trouble if you wait until the last week before the deadline or not. So I would advise you to start early. Right, so let's look at where we left off last week. And I wanted to do this to get a link to jump to the thing, but I saw that there's a problem because we left a definition, well, a declaration without a definition. So it's saying there are still unsolved things, and you can add this option at the top of the file to allow you to load files that still have open metas. So that might be useful for the project because the project is split in like 5 files. So if you're seeing these kind of errors, don't be afraid. Just slap that option at the top. And then even though they are open metas, you can still import that file from another one, which allows you to work non-linearly, right? Because some of the easy marks might be at the end actually, or in the middle. They're not all at the start because we're going topic by topic, basically. Okay, so where we left off last week, we had defined various flavors of appends, although this is not appending, this should have a different name. But basically we said this is the sensible one. And then we left with a cliffhanger saying, well, if we have a notion of pairs of things, we should be able to take a list that was built potentially by appending 2 lists, or at least the size is telling us that it could have been built this way, into its first component and its second component. And we had said that our intuition was that there's not enough information in this type to tell you where the split is, because whether that list is empty or not, well, if it's empty, okay, there are not many choices.
Yeah.
But if it's non-empty, you don't know whether the split starts here or the next value over. So then we wrote this thing as a hint that we're probably going to want to match on M first.
Yeah, so you'll notice. You would have noticed.
Yeah.
Right, so you notice this one's purple, this one's black. So this is actually a pattern variable. That is the thing, and you can call it whatever you want. This thing M here is reference to this M in the type. So it's saying, it's using the name to access the normally hidden thing. It's saying, give me access to the thing that the type calls M, and here I'm also going to call it M.
Yeah. But I was just going to remove it temporarily. Even if you wanted to just inspect X's, you would get the scary message telling you, I'm not sure if there should be a case. So as we told you last week, ACTA only generates the cases that make sense, but it's not always decidable whether a case makes sense or not. And instead of over-approximating or whatever, ACTA is just really strict. It's like, I'm only going to generate things that make sense. In this case, I don't know. I don't know whether this one would make sense in that whole. Because remember, plus is an arbitrary definition that we introduced just a few lines prior. And so when we want to solve that kind of equation, so if I'm using the empty list n, then I know the index should be 0 because the length of the empty list is 0. So I should be having a solution for 0 equals m1 plus n1. It renamed the things, but basically this shape should be the same as 0. And because we know addition, we know that there's a solution, and a unique one, actually, you pick m equals n equals 0, and then you're done. But plus is an arbitrary definition here. ACTA doesn't know anything about it except for the equations we gave before. And so there's no guarantee from ACTA's point of view that this is first a solution and then the only one.
Yeah, To give you more of an intuition for what's going to work and what's not going to work, the equations Agda is happy to solve are the ones which relate constructors of data types. So it knows that different constructors make things that are definitely unequal. And it knows that if it sees the same constructor on both sides of the equation, that those can be equal if their components are equal. So it's happy to say 0 is not successor. It's okay to say 0 is 0. And it's happy to say successor of A equals successor of B, provided A equals B. So it's only the constructor, the fragment that's made of constructors and variables. That's completely straightforwardly tractable. Anything else is too hard.
Yeah, as soon as you're introducing functions, you need to somehow compute the pre-image of the function, and that gets really hairy really quickly. So
yes, I mean,
we don't even attempt to do it.
When you write down the equations, you tell Agda how to run your program forwards. To solve equations like that, the one we just saw, Agda would have to be much better at running programs backwards.
And that's,
if that's what came out, what went in. That's a really hard problem. So it's not, just trying to manage expectations.
Yeah, so we can't even split on it. So actually, that's a good sign that this was probably the bad approach. Or our definitions were wrong. It always depends. It could be that your definition is not ideal. So as we said, what we want to do is actually inspect M, and depending on what its shape is, we'll decide what to do. So if M is 0, then we know that we are taking a prefix of size 0 here, and we're returning the rest here.
Yeah.
And would you look at that?
Yeah.
Here we had a size of 0 plus n. It computed away to n. So we have exactly all the bits we need. Search even finds the solution. So we return the empty prefix and then the whole less than as a suffix. And in the case where m is non-empty, is non-zero, then this will compute to successor of m plus n. So this is what you see here, which now by definition of list n means that we're allowed to match on list n because we've discovered that its length is at least 1, meaning that we know for sure there's a head and a tail. So we can split that x's now, and it's accepted. Okay? And so now what we see is that we have a head, we have a tail of size m plus n, and we want to generate this thing. So how do we proceed? Well, we're gonna call ourselves recursively, x's. So this is really scary. Now it's a lot of yellow. And here you have a hint of what's happening. So it's telling you like these scary things are unknown, and they're called m and n with some suffix because they were automatically generated variables and so on. And it's telling, I don't know what these should be. And that's why you're getting a bunch of yellow here, because it's not quite sure how to pick the m and the n in the recursive call. And why is that? Because the only constraint that we have is that we can feed x's here, but that means that we're feeding something of size, oh, it's off the screen now. Oh no, I need to look in the hole, I guess.
Yeah.
Of size m plus n, and then the kind of constraint that you have is m plus n equals m prime plus n prime. But as we've seen before, if you add 0 to the left or to the right of a number, it gives you back that number. So in a sense, it's not necessarily the case that m equals m prime and n equals n prime.
Yeah.
If you have n plus n equals m prime plus n prime.
Plus is not injective, you know? 2 plus 2 is the same is equal to 3 plus 1, but 2 is not 3. And
so it's again this issue of running plus backwards. Like even if it's stuck on like a lot of unknowns, it's still not the case that we can just do some unification under the plus.
Yeah, so this is genuinely ambiguous. Agda uses background color as a kind of health check.
Mhm.
And the thing to remember is that yellow background means suspicious, whereas brown background is very definitely this is shit.
Mhm.
And yes, it is an intentional reference to bodily fluids, and that's entirely my fault.
But so there's one thing we do know, however, well, there's a few things we know. So we know this is the goal, but we also know that this induction hypothesis, that's why I call it IH, has the shape a given list n times a given list n. And we know that times is a record with a unique constructor. It's defined just above. Too much scrolling. Oh. It loves to just jump around so that we don't have the whole code on the screen. Okay, the whole of the code. So it's defined as a record with a single constructor. So it means that we could actually match on this and extract each of the components, the first and the second one. So we can say I have a prefix and I have a suffix that are the result of computing this induction hypothesis. So now I have my prefix, I have my suffix, and I have my goal. And it looks like I should be able to put the right bits in the right places. So let's see, if I see Control-C, Control-R for refine in the goal, it's going to introduce that comma, which is the constructor for the times types, because it's, again, a unique constructor, so there's no choice. And here I need to build a suck of something. Well, I know how to do that. I need to use my cons constructor. And now I need to feed in a head. I just extracted one here. And it's, if you remember, appending is putting things on the left and things on the right and respecting the order. And here the head is flowing all the way to the left. So like we're doing the right thing morally. And then here, what do I have? I need a list SM, and I have two results that I computed by induction hypothesis. So one thing, the right thing to do, of course, is to put the prefix here and to put the suffix there. Because I'm trying to undo appending, so I'm doing it in an order preserving way. And you can see now that all of the yellow is gone. Why is that? Well, because if you look, we're looking at the holes, right? So this one, for instance, here you're saying, oh shit, everything is solved here already.
Yes. Because
Okay.
Agda is not, Agda actually does try a little bit harder.
Yeah.
But,
so if I look at the hole here, I'm looking for a list n of something. And when I put the prefix n, then I'm saying, well, this M140 should be equal to that M here. And here, Agda was not able to figure out what M I wanted. But now that I'm saying these two should be equal, it's saying, oh, okay, so the implicit argument that I called M140 in here is actually exactly that M that you have here, just because of the constraints all being solved. So even though M is really the defining parameter here, you don't even need to mention it when you're performing the recursive call, because through just solving the constraints, it's able to know what to do. And oh, this one is, yeah, that's a valid solution, but
it's correct, but ugly.
And not performance, yeah.
Right, so this indeed validates the decision to make M implicit. So what we're saying is that at use sites, M and N are determined by what's demanded. And that, you know, we look at wherever the customer wants the split to happen, that's where the split happens. And that's being used to figure out some genuinely extremely important runtime information that you don't have to work to get right.
And just to double check, if we had put things in the holes but backwards, what do you think would have happened? You're thinking about the constraints. So here we have m, and it's getting solved to n because we're passing in this thing. Well, this thing is the n underscore 100 whatever. And this is n underscore, this has type m underscore whatever, and it's been put in the hole where we're expecting an n. So we're solving these things, meaning that this should be of size n and this of size m, meaning this should be of size n plus m, but it is actually of size m plus n. So it should be a type error saying that.
Let's just see.
It looks weird. And it's a bit too clever.
Yeah, so the thing is that it's not a left-right split, but it is reasonable to imagine that you could cut x's in the right place for these things to fit together properly. However, Agda doesn't know that bit of algebra that would be required to check that those equations work. You know, Agda doesn't know that plus is commutative.
Yeah.
Agda only knows how to add numbers.
Yeah. But it's a bit too clever for its own good because the error message it's returning is not even mentioning the fact that we're comparing these two pluses, which is unfortunate in this instance. But okay, but that's the correct code. The type checks. We're all happy. Okay. Let's go to today's contents. So last week we were looking at programming in a Haskell-inspired manner, trying to rule out the impossible cases. And this week we're going to be looking at our first proofs, basically. So sometimes you are able to put the invariants that you're interested in your data type definition. So when we define list n, we're saying I care a lot about the length of my lists. And when I'm combining them, I want to be able to insist that they have the same length and so on. But sometimes there are notions that you cannot put as part of the invariant, otherwise the data type just becomes too complicated. It's something that is useful to observe, but it's not something that's useful to internalize. And I think, last week I was already trying to write some unit tests involving equality. So this is the thing, or maybe you wanted to define equality.
I don't know. I don't want to type that symbol.
Oh, yeah.
I don't even know how.
So it's / equal.
Okay.
And then, let's do a simple one. So what does it mean to be equal? Well, we're going to talk about some values. We could define equality just for the natural numbers, for instance, but then it's not very reusable. We have polymorphism in the language, so we might as well say, I'm going to define equality for an arbitrary type. And then because the value I'm going to be mentioning and saying this value is equal to this other value has a given type, we can always assume this type can be reconstructed. It's like, by seeing this thing and knowing what its type is, this value is implicitly filled in. So that's why I'm saying for any type whatsoever, and a value of that type, I can define what it means for two values to be equal. And now this is where so these were our parameters. We're going to define an entire family of types, of proofs that are that any value is equal to A.
Yeah.
So now
we're defining the property of being equal to little a.
Yeah.
But you need to finish writing that type signature otherwise.
Yeah, so just like we saw in list n, the parameters are constant throughout the definition, so that's your type of values in the vector or in the list n. And then the indices can vary per constructor. So in this instance, we're going to be defining the family of things equal to A, but now the thing, the other side of the equation will vary per constructor, right? Because we're going to be explaining how you can be equal to A. So it becomes an index rather than being another parameter. So it's always this distinction you need to have in mind, constant versus varying. And when is an arbitrary value of type A equal to little a?
There's only one value in big A that's equal to little a, and you will not be particularly surprised as to which one it is.
Yeah. So we call this REFL for reflexivity because it's any value is equal to itself. That's sort of the fundamental property of equality. And this constructor has type A equals to A. So that is to say that you can see it as a proof that A is equal to A. It looks like a very boring proof, but as we saw with list N, right, where we have constructors whose return index is always 0, successor of something, that doesn't mean that then your assumptions always need to have 0 or something, or successor of something as their index. They could be an addition, they could be anything you wanted. So it's not because here the return index for that one constructor is little a, that it means we cannot formulate equations over arbitrary things. They may or may not be true.
So there's something to say here. What this means is that when it comes down to it, AGDA is only willing to accept things are equal if it can see that they're equal. And it's willing to do any amount of computation to try and see those things are equal. But it doesn't do anything cleverer than that. So there will turn out to be things which are kind of philosophically, morally equal that AGDA is too stupid to accept are equal. This is always going to be a slightly disappointing presentation of equality. And I'm sure we will run into that sooner or later. But for things like numbers, it's perfectly adequate.
Well, yeah, so when you have concrete numbers and operations over them, the operation can just run because all of the values are known, so you can just evaluate away, and hopefully you can prove that they're equal. So so rather than redefining stuff and so on, okay. Now that I've imported this thing, it's clashing with the standards, standard library definitions. So I've started slowly introducing more and more standard library definitions because it's a bit silly to always redefine everything from first principles once you've understood how it works. Oh, okay, so
Yes.
So if I look at the goal here, just loading the file, it's telling me I need to prove that 5 is 3 plus 2. But if I look at the type in the whole, or maybe there's another, oh yeah, okay. So implicitly, it's always doing a little bit of simplification when you just look at the goal. If you do Control U, Control C, Control comma, so this is just putting Control U in front of the usual show me the goal commands, then it's not doing any normalization. So here you can see we have the origin one. And if you're doing double Control U, I think it's going to do something else. Oh. It's going to normalize even more, I think, but here we've already reached like the end. So I should be able to use REFL here. It's brilliant.
Yeah, so this is showing that they don't have to say exactly the same thing. They just have to compute to the same value. So it's willing to do arithmetic, operations like arithmetic, but doesn't do algebra.
And then let's try it in here. And it's telling you that 17 is not the same as 42. And so the expression REFL doesn't have this type. And how is it saying this? Well, 17 starts with a successor, 42 starts with a successor. So they're both constructors, they're both the same constructor. So you can just peel it off and compare the predecessors. So then you have 1641, doing it again, all the way to here you have 0, and here you have 25, I think, probably. And then eventually it's like, well, these are not equal because one is 0 and the other one starts with a successor. Okay. And better than that, actually. So we'll see, I think next week, this thing. Whoop. But, whoop, this. Oh, nullery. Whoop. Yep. So it's even more powerful than that. It can see that they cannot be equal. So this is saying it's not the case that these two are equal. We'll see next week how you can define this, but this is basically valid proof of the fact that they are different.
I don't know if we've seen this notation yet. There are two ways to define a function in AGDA. There's the usual way, which is to look at the input and say what the output is. But there's another way in very special cases, which is to say, this can't be happening to me. I don't have to give an output because there's no chance of ever getting an input. And that's what we're saying here. See, this type is defined as, this is a definition. So not really means function to the empty type. So what we're saying here is we are offering to convert any proof of 17 equals 42 into a proof of false. And that's a reasonable offer because no one is ever going to pony up a proof that 17 is 42, so we're not going to get called on it. And that's what this is saying. This is telling the input to go away. Right? I don't have to produce an output because the input is impossible.
Yeah, so there's an entire field of like semantics of functional programming languages that looks at the types of programs and seeing them as sort of games, right? So if you write a program and you have a bunch of assumptions or arguments to it, it's whoever is calling you's responsibility to guarantee that they can actually pass values for this. So in a sense, it's giving you stuff that they claim is true, and then it's your job to deliver on the outputs. But you can deliver on the output or just call people out on their lies in the inputs, because they were supposed to provide these inputs to you. And if one of the inputs just cannot be built, you're entitled to call them out on their lie and just win the game this way.
So as a programmer, you're constantly having a fight with the devil. You know, she's trying to choose the inputs to your function to mess you up. And you have various ways of fighting back. And this is one of them.
Do you want to do John Major equality?
No, I don't.
No? Okay. Because, I mean,
we could mention it, but, right. So you'll notice here that the only things we consider as kind of what's it like to be the same as little a are elements of A. And that's to say, you're only allowed even to propose equations between elements of the same type. You're allowed to offer the suggestion. It's a reasonable thing, according to this, to propose the equation 17 equals 42. You can't prove it. Indeed, you can disprove it. But you're allowed to say it. It's a thing. It's a reasonable thing to bring to the discourse. Whereas this formulation of equality does not allow you to say 17 equals hello. You can't prove it, you can't disprove it, but more than that, you can't even think it. And once upon a time, I was writing my PhD thesis. And I began a sentence it is important that the two things being proposed as equal values are of the same type because. And then I thought, what is the end of that sentence? Because that's the way it's always been in the libraries about stuff that I've used. Because that's what my elders and betters decided. What would happen if we just allowed people to say 17 equals hello? Would anything particularly bad happen? No. I mean, you should definitely not be able to prove 17 equals hello. That's, yeah, we are absolutely solid on that. But, you know, is it such a terrible thing to be allowed to say? And it occurred to me that maybe it was all right. So I reformulated equalities to allow that greater freedom in which equations were thinkable. And some things got nicer because of that, and some things got less nice because of that. And this version of equality, I named it after the former Conservative Prime Minister, John Major, who took over from Maggie Thatcher. And when he took over from Maggie Thatcher, he tried to pretend to be nice. And he said, we must aspire to some sort of classless society. So he was trying to widen people's aspirations to equality without actually changing the reality that, you know, the rich have all the money and the rest of us don't. So yeah, that was, because in the end, we are equal only to ourselves. So that was a joke at John Major's expense, which I put in my PhD thesis and which got picked up in the libraries of various other systems based on these ideas. And if you look on John Major's Wikipedia page, you'll find that in the section on honours and tributes to John Major in public life, you'll find that my choice to name a definition of equality after John Major is one of the things which is listed, and it wasn't me who put it there.
Right, so if we look at 17 equals hello in Agda, well, Agda just complains and tells us, you told me that whenever you had a little a of type A, you were going to give me another value of type A, but here you've given me a string when I was expecting a natural number. This is nonsense. You can't even like mention, like discuss that thing. But of course, the whole point is that these definitions, whenever you introduce a new data type, the choice is yours, right? Well, there are a few rules that you need to abide by, but other than that, the choice is yours. And so if we decided to model equality this way, we could have actually decided to model it another way.
You're doing it? Okay, yeah, fine.
This
Just
way.
slightly wobbly equality.
So it starts the same. I've got some implicit A because I can reconstruct it from the type of little a and so on. But now I'm willing to accept an arbitrary B here. And for an arbitrary value of type B, I will have a proof, potentially, maybe. Okay? And then what's the one constructor for it? But as Connor was saying, at the end of the day, you're only equal to yourself. So that doesn't change. You still have a wobbly equal to A. But now you can actually formulate the thoughts that 17 might be equal to hello. And if we move this down a little bit, we can actually, yeah, that's the right spot for it. We can actually prove that it's not the case, that these two things are equal. Oh. Oh, yeah, so, oh. Oh. Oh, I know.
Oh,
What?
I don't know what's going on there.
Is it still?
But you need to switch on injective types or whatever it's called.
No?
Nope, that's weird. It's just
Well,
it's fallen into a mysterious void. I mean, philosophers disagree about the status of 17 equals hello.
yeah.
Um,
I mean,
um,
I guess if you're using Gödel numbering or something, you could. Okay, so it turns out you cannot prove that
right.
these two are
So
this
yeah,
thing. At least this way. There are other techniques to
right.
prove that
Yeah,
things are not
and
equal.
so this is actually fairly true to the plan, because the whole thing is that equations between things of different types should be harmless to state because they're useless. They don't. They never do you any good, right? So crucially, in particular, what's equality for? I mean, it's not meant to be a deep philosophical question, even though of course it is. But the point of equality is to be able to substitute one thing for another. This is, goes back to Leibniz. If x equals y, then things which are true about x better be true about y as well. So that's to say, the point of equality is to facilitate substitution. And we definitely never want to be substituting hello for 7.
Do you want to do congruence?
Okay.
Yeah.
Right. So, and you want me to call it Kong, do you?
Yeah.
Right. So, way back many centuries ago, there was an Arab mathematician called Al-Khwarizmi. And his name is what gave us the word algorithm. He invented one of the early algorithms for solving quadratic equations. The thing that you learned as the quadratic formula is how do you arrive at it? You do Al-Khwarizmi's method. You may have learned a thing called completing the square. Does that ring a bell? That is the eponymous algorithm. That's Al-Khwarizmi's algorithm for solving quadratic equations. And it works by doing the same thing to both sides of an equation. That's the thing you learned is that if you've got an equation which is true, and you do the same function to both sides of the equation, it stays true. Let's say that. So we're saying if we've got two function types and a function from S to T, and if we've got two values, x and y in S, and the proof that x is, let me see if I can type, is equal to y, then we ought to be able to get our hands on a proof that f of x is equal to f of y. By the way, the idea that if you do the same thing to both sides of an equation, you preserve the truth of it, is called the principle of balancing, or in Arabic, algebra. This is where it's from. So yes, I did that already. So you see, at the moment, not in scope, but we know they're there, the curly braces, we've got a proof Q that x is equal to y. And we're asked for a proof that f of x is equal to f of y. Now, here's an important thing that doesn't work. I could say, well, you can see it's true, can't you? Doesn't go in the hole. Hang on a minute. X is not y. These are two variables. The fact that there's some value of type x equals y in the context does not have the same force as the definitions you make when you write a program. 2 plus 2 computes to 4, and that's why you can say REFL to prove that 2 plus 2 is 4. X does not compute to y. X is a variable that just sits there being, well, I don't know what it is, I'm stuck on X. And y sits there being stuck and not computing to anything.
You can try putting REFL back in just for the error message. So if you look at it, it's not the same notion of equal that's here. Because we defined the triple bar equal. It's just an arbitrary definition we introduced. Agda doesn't know anything about it. This is its internal notion of equality, which is to decide whether two things are equal modulo computations. And so there's no reason why our arbitrary family should have an influence on this. So it doesn't, actually.
Right. So what we have to do is to find a way to actually make use of this piece of evidence that x is y. And we already have seen how to do that. Remember when we defined tail for lists indexed by their length? And it said, well, not only is the return type of cons a successor, the predecessor is actually the tail length we want. It's actually willing to solve equations. So if I pattern match on Q, let's see what happens. The goal has now changed. There is now no longer even a y in scope. What it has figured out is that the only way there can have been a proof that x equals y is if that proof was REFL, the constructor, and that means x and y must have been the very same thing. So it actually performs the substitution. So that's what happens when you pattern match on a proof of an equation, is that you get the substitution to happen. And now we can say...
if you explicitly introduce x and y in here, it will actually tell you that it's assigned like y to x or the other way around.
Shall we try that?
In the goal, yeah.
Okay, let me rewind.
Because these things are silent, so we're not really seeing what's happening to them when we're matching. But if we make them explicit...
Okay, so they're now explicit. And I do Control C to pattern match. And you see that something wonderful has happened. There is only one x here. And you see there's the same x here with a dot. And what that dot means is, I'm not asking you, I'm telling you. It's not saying, oh, whatever this is, I want to call it x. It's saying, I insist that the only thing that can possibly be here is x. So it's documenting that some deduction has happened, that it is figured out that the thing in this position must be the thing in this position. That's what's going on here. And this is one of the things that can happen with dependent types, is you get things which show up left of the equal sign in a pattern matching definition, which don't look necessarily, they don't even have to be constructor expressions. They're not actually going to be used as patterns to match on operationally because there's no choice for what's in that position. So this is telling us we've deduced this thing, and now we can solve the goal with REFL. So that was a revelation that we can really use the ability to look at one thing. So the operational behavior of this is the same thing you would expect. You're pattern matching on a data type. You're looking to see which constructor it is. There's only one constructor possible. And if that constructor shows up, then you can deduce that these two things must have been the very same thing. And that's something that happens in a dependently typed situation that you don't get in vanilla Haskell anyway. Haskell's moved in that direction in recent years. But there we go.
Yeah, this is also telling us another very important thing about ACTA functions, right? So here we're saying for an arbitrary function from S to T, if you have two values you can prove to be equal, then you know the results of applying f to x and f to y will be equal. So that means in particular that you know for a fact that a function can never inspect the structure of the expression its argument was built with. You can look at the constructors because these will not move through computation. If something starts with a successor and you evaluate it some more, you know you will still get the successor at the front, right? Because it's non-zero, it's going to stay non-zero no matter how much more you evaluate it. But if something starts with a plus, the plus might go away by computation. And therefore, this is telling you that you can never observe that x was built as m plus n, for instance. So sometimes in some languages, you can actually look at the structure of the pile of functions your argument is built with, and then do something special with it for debugging or whatever. But here, the notion of equality tells you that there's no way for you to look at it, which is both a blessing because it means that all of your functions are well behaved and you can prove like really sensible things about them. It's also a curse, meaning that you cannot write these type of debugging things because you cannot inspect how that value was built. Unless, and this is a very common approach in type theory, if you actually care about the structure of your argument, just write it as an inductive type. So if you want to know whether something was built using plus or times, etc., you declare a small language with constructors corresponding to plus and times and so on. They have the semantics that you intend for it to have, which you can define. But because they're abstract syntax trees, you can then inspect them. But you have to be a bit more explicit about your intentions, basically.
Yes, it is not the case that functions are like considered as being made of code. That's our little secret, that functions are actually built by programming. And if you want a kind of function that is inspectable in that way, you actually have to build a whole coding system that says, okay, yes, here's some code and I can explicitly evaluate it to get a function. That's doable. Lots of other things as well. I think we're running out of time.
Yeah, but it's a good stopping point. So.
Yeah, except to note that 0 is the neutral element of plus.
Oh, yeah.
So let's not prove something which isn't true.
Yeah.
So you can change